Hello and welcome to this next lecture on the course on pattern recognition. So, we looked at linear models for classification regression. That is what we have currently been considering. We are looking at learning of linear classifiers and linear regression models, and we looked at various methods. We looked at perceptron, we looked at linear least squares, various variations thereof, linear least squares with regularization term, then logistic regression, special linear discriminant, whole set of methods of learning linear classifiers and linear regression functions we have considered. And so far we have mostly concentrated on the two class problem. That is, when we presented algorithms for classification, all the algorithms are only for two class classification problem. Similarly, when we discuss linear regression like least squares, we only consider the case when the target values are real valued. That means, we are only learning a real valued function over some arbitrary d-dimensional space. Okay. So, we looked at only real valued functions in case of regression and two class problems in case of classification. And towards the end of last class, we briefly saw how we can generalize this easily to multiple classes in the classification case and vector valued functions in the regression case. So, we will start with that again this class. We will briefly review how the generalization goes. Then we will look at the generalization of logistic regression, which is somewhat little more complicated than simply generalizing least squares method for multi-class classification or vector value regression. Okay. So, to start with, we saw in the last class that learning a vector valued function using least squares approach is a very straightforward extension. What does learning a vector valued function mean? That the target values themselves are vectors, right. So, it means that we are given training data xi, yi as usual, n training data, where xi is in some RD as usual, but now yi itself is a vector. Let us say is a m vector, it is an Rm. So, there are m values. So, let us say yi has components yi1, yim, and we want to learn linear models for each of them. So, what does that mean? We have each component of y will be predicted by a linear model, which means we need to learn m vectors wj and m scalars bj, such that the jth output or jth target yj can be predicted as wj transpose x plus bj. Right. So, when viewed like this, it is simply a question of solving m number of linear least squares regression problems separately, because the wj and bj that are involved in predicting the jth component of the output have nothing to do with the w's and b's in predicting any other component of the targets. So, even when the target is vector valued, essentially each component of the target value y has to be predicted using a linear model. Each of the linear models will have its own w and b. So, it is essentially simply solving m number of least square regression problems. Of course, we can put the whole thing into a vector matrix notation, but except for notational complexity, it does not give us any insight. So, the substance of this, which we have seen already last class, is that generalizing linear regression using least squares approach to vector valued functions is absolutely straightforward. It is just simply learning, instead of one w and b, learning m number of w's and b's, right. Each have their own targets. In a similar way, we can extend linear least squares approach to multi-class classification also. Okay. What does this mean? Okay. To go back to how we started last class, for multi-class classification, right in the beginning of the course, we mentioned that essentially the two class problem is the fundamental problem. If we can solve the two class problem, we can easily solve multi-class problem, at least in principle. What does in principle mean? That we can have many two class classifiers to solve a multi-class problem. As I mentioned, there are essentially two approaches, which may be called one versus rest or one versus one. What does one versus rest mean? Suppose I have got classes C1, C2, Ck. So, I learn a two class classifier which classifies C1 or not C1, similarly C2 or not C2 and so on. So, I will have k number of 2 class classifiers. I give the new once I learn them. So, for each of them I know how to make the training samples given the original training samples, and once I learn all the classifiers given a new pattern, I will ask is it C1 or not C1, C2 or not C2. Hopefully, if only one of them says yes, then that is the class that can be given. In the 1 versus 1 approach, I am learning 2 class problems as C1 versus C2, C1 versus C3, C1 versus C4 and so on. The main reason for considering 1 versus 1 as opposed to 1 versus rest is the issue of sufficiency of training samples. Suppose you have 10 classes, each with 100 training samples. So, total you have 1000 samples. When I do 1 versus rest, each of those classification problems will have 100 samples of one class and 900 samples of the other class, because it is C1 versus not C1 and so on. So, the sample sets are heavily unbalanced, the training data, which makes learning a little harder. As opposed to that, 1 versus 1 approach will always have balanced, roughly balanced training data set. So, it is a little easier in terms of stability of the classifier learning algorithms. These are very often used. Many standard packages for multi-class classification use one of the 2 approaches. But however, at least in the linear classification case, there are better methods than this. This is because neither of these approaches is wholly satisfactory to tackle a multi-class problem. That also we see in last class. What happens is that this kind of classifiers always have undefined regions in the feature space. Intuitively, if I learn C1 versus not C1 and C2 versus not C2, I give a new x to C1 versus not C1 classified, it says C1, and I give the same x to C2 versus not C2 classified, it says C2. Then should I take C1 or should I take C2? That is the issue. So, in particular, so if I have this hyperplane I learned for C1 versus not C1, this hyperplane I learned for C2 versus not C2, what happens here? Right? These points, because these are on one side of the side of C2 as well as the side of C1, thing is not clear. Right? So, there will always be regions in the feature space where the classification is not defined, right. Because ultimately the classifier has to be a function of the feature space. This is not fully satisfactory. Same thing happens when we do Ci versus Cj, right. I have 3 classes here, C1 versus C2, C1 versus C3 and C1 versus C2. Depending on what kind of hyperplanes are learned, it is always possible to have region in the feature space where C1 versus C2 classified may say C1, C3 versus C1 classified may say C3 and C2 versus C3 classified may say C2. So, I can't even take majority vote, right. So, there would be such undefined regions in the feature space. So, in principle both 1 versus rest as well as 1 versus 1 are not completely satisfactory solutions to the multi-class problem. And we have seen last class that one way of generalizing linear discriminant functions is to have, for a k class problem, to have k discriminant functions. Okay. So, the idea is we will have k functions, call them GS, each of them is a linear function, GS of x is WS transpose x plus BS, S goes from 1 to k. And then how do I use these k functions for classification? So, given a new x, I will ask which of the g's has the highest value. So, I will assign x to class Cj if Gj of x is greater than Gs of x for all s. Of course, it is greater than or equal to. So, there may be more than one j that satisfies this, right. So, maybe G1x and G2x have the same value and they are better than all the other values, then should I put it in 1 or 2? This is not as difficult a problem, because we can have some arbitrary way of breaking ties. For example, we will say that if more than one j Gj satisfies this, I put it in the class with least index, right. Now, while the complete correctness may be okay or not okay, at least this is a proper function. So, as long as we have a simple rule for breaking ties, having k functions like this will completely specify a linear classifier in the multi-class case. You may recall that this is exactly how we generalize the base classifier to multi-class case. It also had k such discriminant functions, and you put x into that class whose function had the highest value on x. Now, how do I learn these k functions? As we seen briefly in the last class, we can learn these k functions simply by doing a vector value regression, right. So, to learn the k class classifier, we need to learn the k functions GS, each is a linear function. So, the way we do it is to make the class label itself as a vector. Instead of making the class label take values 1 to k, we will make the class label take k dimensional vector values. So, that class 1 will mean 1 0 0 0, class 2 will mean 0 1 0 0 0 and so on, right. We have already encountered this kind of representation while we are doing estimation of densities. So, a similar kind of representation will use. So, if xi is in class Cj, then the corresponding class label yi would be a k vector with the jth component 1 and all others 0. Right. Then the learning the k functions is same as a linear regression with vector value targets, right. So, now using our earlier method of doing regression with vector value targets, we can simply run least squares to learn the k class classifier. Okay. So, this is one method of doing linear discriminant analysis for the multi-class case. Okay. So, we learn these k functions using least squares by essentially making our targets, which are class labels, into vectors. Okay. Now, let us move on the other algorithms that we consider. So, this what we said so far generalizes linear least squares method both for multi-class classification as well as vector valued function regression. Now, let us look at the remaining ones. We will consider logistic regression, we had considered facial linear discriminant and so on. So, let us look at logistic regression, how to generalize it to multiple case. So, let us just recall what is the main idea of logistic regression. Logistic regression essentially uses the linear least squares, but instead of using a simple linear model W transpose x, it uses H of W transpose x, right. So, the idea is that you approximate the posterior probability. Recall that we are using Q's as the symbols for posterior probability. So, Q1 x is the posterior probability of class 1. So, we want to represent Q1 x as H of W transpose x plus W naught for some W and W naught, that is what we will learn ultimately, where H is the logistic function, H of A is 1 by 1 plus exponential minus A. Right. And you see this logistic function, of course, we can have a small parameter that multiplies A, we can have 1 by 1 plus exponential minus eta A, and eta determines the slope at 0. But essentially the logistic function, as you see in last class, if A is large positive, is close to 1, A is large negative, is close to 0. So, essentially it is a kind of a continuous approximation to the step function, right. So, basically step function is what we want, and we are using a continuous approximation. So, in the logistic regression, the idea for the two class case, the idea is to find a W and W naught to minimize your usual criterion function of least squares, where instead of taking the target as a linear function W transpose x W naught, we are taking it to be H of W transpose x W naught. H is monotone continuously differentiable, and hence using LMS algorithm we can easily learn this, right. We take the targets to be 0 and 1, and as we seen while studying LMS algorithm, the least squares approach is easily generalizable to H of W transpose x W naught as the model function, as long as H is nice monotones differentiable. So, essentially on this function we do a gradient descent to learn the optimal W and W naught. Having learned W and W naught, we simply use H of x transpose W star W naught as the posterior probability of class 1 for a given feature vector x, and that is how we implement the classifier. Okay. So, this is the basic idea of logistic regression. So, let us try to extract the essence of this idea. So, what is it that you are using, what part of it is specific to two class. Okay. It's the way is looked at, because there is a H of W transpose x plus W naught, it's not quite clear how I can make this, how I can easily generalize this into multiple classes. So, to get a feel for how I can generalize it to multiple classes, let us ask exactly how am I using the 2 class restriction or 2 class fact in this formulation, right. So, the motivation, so what is that are we doing in the logistic regression? We are approximating the posterior probability by this logistic function, right. Now, why is it a good idea to, why do we think we can do it? The reason we think we can do it is that I can always write the posterior probability in a 2 class case as f1 x p1 by f0 x p0 plus f1 x p1. This is simply by base rule. Q1 x is probability class is 1 given x. So, I can use base rule to say the density of x given class 1 into probability class 1 by the normalizing factor. Now, this I can write like this. Essentially, what I am saying is you multiply, you divide both numerator and denominator by f1 p1. So, it becomes 1 by 1 plus f0 p0 by f1 p1. Now, that I can write like this 1 by 1 plus exponential minus j, where j is given by this. Okay. So, I can always write any posterior probability in 2 class case as 1 by 1 plus exponential minus j. Of course, the only question is, can I write j to be j is of course a function of x, function of the feature vector x, because j is given by this. If this function of feature vector x, will it be linear, right? For the class of densities where a linear approximation to this function is nice, we can use logistic regression. Okay. So, that is the basic motivation for using logistic regression in the 2 class case. So, for the multi-class case, what we will do is, we will write the base rule for the posterior probability for any class like this. There will be more than 2 terms in denominator now, and then derive a appropriate function, not the logistic function, but some other function, that is the right way to approximate it. So, before we go there, let us while this motivation is clear from base rule, it may not still be quite clear where the 2 class fact is used. So, let us understand this. In the 2 class case, essentially what is that we want to know? We want to know which of f1 p1 and f2 f0 p0 is greater, right. Given an x, if you want to actually implement the ideal base classifier for 0 1 loss function, the idea is that we calculate f1 x p1 and f0 x p0, these are proportional to the corresponding posterior probabilities, and hence whichever of these 2 is greater, we can put it in that class, right. Of course, in the logistic regression, we are somehow approximating some proper function of these as a linear function, because we can only learn linear functions. So, this is done by looking at, so if I want to know which of these 2 is greater, I can take the ratio, take the log. So, whichever one is greater. So, if the numerator is greater, the log will have positive sign. If the denominator is greater, the log will have negative sign. So, whichever is greater can be ascertained by taking sine of this, right. But sine of this is a discontinuous function. We do not want to work with discontinuous functions, and hence we use logistic function. Essentially, we want sine of ln of this. We are saying ln of this can be approximated using a linear function. For example, if f1 and f0 are Gaussian with equal covariance matrices. So, if I can approximate ln f1 x p0 x f1 p1 by f0 p0 by a linear function. Now, I want sine of this. Now, that means I have to learn a discontinuous function, because I can't learn I would not like to learn discontinuous functions. I am essentially squishing it using the logistic function. So, logistic function is a kind of continuous analog for finding this, for finding sine of this. So, now in the multi-class case, what do I have to learn? There are not 2 of them. If there are only 2 of them, I can take the ratio and log, because there are more than 2 of them. We want to find with the maximum of some k numbers, fi x pi, f0 x p, say f1 x p1, f2 x p2 and so on. Calculate all the k numbers and then ask which of these k numbers is large, right. So, we essentially have to find maximum of these k numbers to decide which class to put in essentially. So, which means we need a function. Maximum also is a non-smooth function, not differentiable. So, we essentially need some smooth function to approximate the maximum computation, right. That is essentially what we need to generalize the logistic regression to multi-class case. So, let us look at a suitable function for this. So, once again start for the multi-class case, let us start with the base rule. So, if I want the posterior probability of class j, I can write it as fjx pj by summation fsx ps summation over s. As I said, because multiple class, the denominator has more terms, as many terms as their classes. We will write this as exponential aj by summation over s exponential as, where as is given by ln of fsx ps, right. So, essentially if as is ln of this, exponential and ln will cancel each other. So, this is same. So, the posterior probability now has a form like this. Earlier it has 1 by 1 plus exponential, instead of that it has exponential aj by summation over s exponential as. And once again what we want to say is a linear approximation for aj's. Aj's of course are functions of x, is a linear approximation for aj's is okay as far as the classification is concerned. So, the idea is once again we want to approximate each as by ws transpose x plus ws naught. It turns out to be okay. For example, if all class conditional densities are normal with equal covariance matrices, what happens is when you take this ln, if it is normal, then I get a quadratic term and a linear term in x. The quadratic term will always x transpose sigma x, that sigma is not class specific. So, that will come out as a common factor in all these things and it will cancel, right. And hence, I can approximate the posterior probability with a function of this form, where each a has a form like this. Okay. So, this is one case where this approximation is exact. Many other cases also the approximation may be nice. So, once again like in the 2 class case logistic regression, the idea is we approximate each of these ASS by a affine function ws transpose x plus ws naught, and you essentially use a method which is motivated by the fact that the posterior probability can be expressed as a function like this. Okay. So, let us go to the details now. So, once again to tie it up with what I said in the previous slide, that we want to look at maximum. If I somehow land all the w's right and given an x I can calculate all the as's, the basic idea is which as is maximum, because I need to compare different qj's, because I need to compute different qj's and pick the maximum of them, because the denominator is same. Essentially given many such as's, we need to find the maximum. Okay. That is why I said what we need is some smooth approximation to the maximum. So, let us define this function. Let us say there is a function g that maps Rk to Rk. K is the k dimensional real equivalent space to itself, where k is the number of classes. So, g is a vector valued function. So, let us say components of g are g1 gk. So, if a is any point in Rk, then we write g of a as g1a, g2a, gka. The transpose, because all our vectors are column vectors. Okay. And for each j, we define gj by this function exponential aj by summation of exponential as. Right. So, aj's are components of a. A is because g's domain is Rk, a is in Rk. So, a has components a1 to ak. Okay. So, this is the g function we define. From what we said in the previous slide, this g function is a good approximation for the posterior probability in multi-class case, right. The posterior probability has a similar structure. So, this function, this g function I am defining, is a good approximation for the posterior probability function. Okay. This g function is known as the Softmax function. As I said, our idea is we need a smooth function which essentially picks maximum of a given set of numbers. The idea is that if I suppose a1 is the maximum of all the a's, then if I divide all the numerators and denominators in Gj by exponential a1, right. So, for G1 it will be 1 by 1 plus some terms, all of them will be less than 0 because the exponential small numbers. Exponential negative numbers, because it will be exponential say a2 by a1, that is exponential a2 minus a1 is greater than a2. So, it is exponential negative. So, we can assume that they will be close to 0. So, G1 of such a would be 1 and all other G's will be closer to 0. So, the idea is that if Aj is the maximum of the components of A, then Gj of A would be closer to 1 than all the other J's, and all the other components of J will be closer to 0 rather than 1. Right. Of course, we can put a constant multiplied to all the Aj's to accentuate these differences, but essentially this function roughly picks maximum of A1, A2, AK, right, because if Aj is the maximum of them, the corresponding Gj of A will be closer to 1, or Gs of A for all other S will be closer to 0. So, this is a kind of a nice smooth approximation to the maximum function. That is why it is called the softmax function. So, the idea is now to use the softmax function for learning the classifier. Okay. So, now we will write for each S, AS as WS transpose X plus WS naught, and we will learn all the WS's and WS naughts. See, earlier I have W transpose X plus W naught, but now I have more than one such vector. So, each vector has a subscript. So, Ws is a vector, and now my scalar, the bias term, has to have 2 subscripts, because earlier we were calling W naught. So, I called it now Ws naught. As we already seen enough number of times, all such affine functions can be once again written simply as W transpose X. We use augmented feature vector. So, essentially we will call it W tilde and X tilde and write Ws tilde transpose X tilde. But as we have been doing so far in this course, we mentally assume that we have done augmentation and use the same symbols. So, we might as well write AS as Ws transpose X. So, each Ws is a vector now augmented with an extra component Ws0. Now, let us capital W be a matrix whose columns are Ws, right. Now, let us say we learn this W, we'll in a couple of minutes we will see how to learn this W, but suppose we learn the W. So, what is its use for us now? If you give me a new X, I calculate G of W transpose X. What is W transpose X? W is a matrix now whose columns are Ws. So, W transpose X will be a vector whose first component will be W1 transpose X, second component will be W2 transpose X, so on, right. So, we are essentially we are getting the ASS. So, this will be the A that we seen earlier, right. So, W transpose X will be the A whose components are ASS. So, G of A will be what? Will be a K vector again, and it essentially picks the maximum of all the Ws transpose X's. So, we calculate G of W transpose X and then put X in the class Cj if the jth component of G of W transpose X is the highest, right. Ideally, if X is in Cj, we want Gj of W transpose X to be 1 and all other components to be 0, right. That is how we want G to be, but in practice we will put X in Cj if Gj of W transpose X is greater than Gs of W transpose X for all other S. But the fact that this G is softmax and hence this is what we want from our W tells us how we can formulate our objective function. Essentially, the W that is good for us is that if X is a class 1 pattern, then G1 of W transpose X should be 1 and all others should be 0. If X is a class J pattern, then Gj of W transpose X should be 1 and all others should be 0. So, this is simple for us. Now, I can think of it as a vector value regression. So, give me a training pattern xi and let us say its corresponding class label is yi. Now, I represent yi as a vector as usual, 1 in its class. So, if I give that as the target, essentially I am trying to learn a vector value function where if x is in class j, then the jth component of this vector value function should be 1, all others should be 0, right. That is my training data. So, this is now how we can formulate a least squares approach for learning W. We will learn W to minimize g of W transpose x I minus y I whole square, right, where x I and y I are our training data. So, x I is an odd power d as earlier, and y I is now a k vector whose components are y I 1, y I k. Each of the components is in 0 or 1 and they sum to 1, right. So, that means only one component is 1, all others are 0. So, the component that is 1 tells me what is the class label of x, right. Now, g is also a vector, and essentially if x I is the jth class sample, then in this y I the jth component will be 1, all others will be 0. So, I essentially want g of W transpose x I to be close to the vector 0 0 0 1 in the jth position 0 0 0, right. That is why this is a good thing to minimize. I did not put half, we can put half, we do not have to put half. I have been putting half so that when you differentiate the 2 will go away, but really that makes no difference. Another thing I want you to notice is earlier we just simply writing g of W transpose x minus y whole square. Now, we can't do that because they are vector valued functions. So, g of W transpose x I is a vector, y I is a vector, that is why I put a norm on either side. So, it is a norm square. Okay. So, this is what we want to minimize. Right. So, let us look at more closely how we are going to minimize this function. So, this is our function, right. We want to minimize over the training data. So, given an x I, my model will say g of W transpose x I as its vector valued class label. Its true vector valued class label should be y I. So, I take the difference between these two because they are vectors, the difference is the norm. Okay. So, because I want to minimize the squares of the errors, I am taking the squares of the norms. Now, we will take the usual Euclidean norm. By expanding this norm, we can simplify our j of W as follows. Outer summation still remains I is equal to 1 to n. The inner one, this norm, recall that both g of W transpose x I and y I are k vectors, right. So, I can write the inner, I can write the norm as an inner summation s is equal to 1 to k g s of W transpose x I minus y I s whole square. Okay. Now, I know what g s of W transpose x I is. So, let us expand that. So, g s of W transpose x I is exponential W transpose x I by summation over j exponential W j transpose x I minus y I s whole square. So, j of course, I wrote j of W, j is a function of all the W s s. So, that is why I wrote it as j of W. So, this is the explicit function. Now, we want to minimize this, right. Yeah, it does not quite look like the earlier logistic regression, it is a very nice form, some h of W transpose x plus W naught minus y whole square, but it is still okay. I have to learn k vectors and this is the relationship. I can certainly differentiate j of W with respect to each of these W s s and then find the W to minimize this. So, for example, we can use LMS algorithm to find W that minimizes j. LMS algorithm, as you know, is nothing but a gradient descent on this j. So, I need to find derivatives with respect to the component W. For example, I can find gradients with respect to each of the W s s and then move in the direction of the decreasing gradients. Okay. So, in principle, this is the multi-class logistic regression algorithm. Okay. There is just one, of course, this can be done, now there is nothing left except that the expression is a little complicated, the gradient descent optimization might be a little complicated, but this completely solves your logistic regression problem for multiple classes. But having said that, this is often computationally a little complicated. Okay. Why is this a little complicated? This is what we want to minimize. The main problem with this optimization is that learning of different WSS are not decoupled. See, earlier, even though say in the least squares case of learning vector valued functions, even though I am learning many vectors WS, each has its own targets and the learning different WSs are completely decoupled. So, it is just a question of running say k or m number of different simple linear least squares regression issue. But now it is not that, because this function has all the WSs mixed inside. Specifically, what does that mean? If I want to take gradient of j with respect to a particular Wj, it involves all the other WSs, right, because of this normalizing term. Because of this term, if I want gradient with respect to W, say W1, then the s is equal to 1 term is what comes here, but this denominator will be there. Not only that, all the other terms in the summation will have W1 in the denominator. So, I have to take derivative with respect to that. So, it will be a horrendously complicated expression for the derivative. So, unlike the case of vector value regression using simple linear least squares, learning of the different WSs in the case of multi-class logistic regression are not decoupled. This can make it computationally more difficult. Because it can become computationally difficult, one sometimes does some approximations. Of course, when you do approximations, you are not you are no longer exactly minimizing the function that you should be minimizing, but often these approximations are good enough. The approximation is based on the observation that basically this problem, the problem that gradient of j with respect to any one Wj involves all the other Ws, all other W vectors, comes because of only this denominator term. And in the original posterior probability model, the denominator term is essentially a normalizing constant. So, the idea is that instead of using all the other W's here, can I use a simple normalizing constant here, right. So, that is the basic idea of the approximation. So, how do I run the approximation? So, I rewrite J f as this. So, this of course depends on all the other W's. I instead of explicitly saying it depends on all the other W's, I simply say some term that depends on the index I, because this corresponds to the ith data sample. I call it some Z I. So, that is how I wrote it. Now, I pretend that the Z I's are constants, right, they are dependent on I, but otherwise they are not dependent on W's. Then if I pretend like that, then if I take the gradient of this with respect to W1, only that s is equal to 1 term in this summation contributes. Similarly, if I want gradient with respect to W2, only s is equal to 2 term in this inner summation contributes. So, once again all my W's will get decoupled. If you use the above objective function, as I said, to do gradient descent on J, what does that mean? If I use LMS algorithm on this, then gradients with respect to different WSs are completely decoupled. So, I can now run this as if I am doing different m number of different individual functional learning problems. But that is not quite true, because the Z I's have to be proper normalizing constants. So, what one does is the following: you have currently some values of W's, use that to calculate the current Z I. Once you calculate Z I, you pretend that Z I does not depend on W anymore, and then calculate gradients. Now, gradients become very simple terms, and use the each of the gradients of WSs for a particular S, use the gradient of J with respect to Ws to find the new value of Ws, do gradient descent individual in each of the Ws, and after each iteration you recompute Z I using the new current values of Ws, right. This way is not completely decoupled, because iterations have to run in step, right. So, after doing one gradient descent for each of the W's, I use all their values to recompute the Z I's, but still the gradient computation is much simpler compared to earlier one, where each of the terms in this inner summation contributes to the gradient. Now, only one term contributes to the gradient. So, computation of gradients becomes simple, and recomputing Z I after every iteration is a small extra computation cost to pay. So, often this approximation gives you a lot of computational advantage. Okay. So, when one uses logistic regression with multiple classes, we either take this and do the brute force gradient descent on this using the full gradient, or we use this approximation and keep recomputing ZIs. Often this is computationally simpler. Okay. So, you can sum up. So, we have seen the generalization of logistic regression in multiple classes. It is a little more complicated than generalizing least squares regression, least squares classification, the simple least squares regression classification. But the basic idea, as we have seen, is instead of using logistic function in the posterior probability modeling, we are using a softmax function, right, which is also quite straightforward. Essentially, a logistic function is used as the as a continuous approximation to the function of sign of ln posterior probability of class 1 by posterior probability of class 0. In the multi-class case, I need to find the maximum of all the posterior probabilities. So, I have to use some continuous some smooth analog of the max function, that is the softmax function. Okay. So, once we see this connection, essentially is notationally complex, but the basic idea of generalization is the same. Okay. Because of this complexity, of course, it is not completely decoupled, but as we seen using that approximation, we can partially decouple it. Okay. So, this gives us the multi-class logistic regression. Now, what about facial linear discriminant? That also can be generalized to multiple classes. Okay. So, once again let us ask, what is the basic idea in the two class facial linear discriminant? The two class case, what we are doing, we are interested in finding a direction, a particular vector W. A single direction can be thought of as a one dimensional subspace. So, it is saying in the two class case, we want to find a one dimensional subspace onto which we want to project the data. Which is the one dimensional subspace we want to take? The idea is to take that subspace where after projecting the data, the means of the two classes have maximum separation relative to their variances. Right. That is the basic idea. So, you want to find a particular one dimensional subspace. This is the two class problem. I want to find a particular one dimensional subspace where there is a proper separation, and this proper separation is formalized as you may recall using that within class covariance, within class scatter matrix and between class scatter matrix. So, in principle, generalizing facial linear discriminant to multiple classes would mean what? For a k class case, we want to find a k minus, in the two class case, we are finding a one dimensional subspace. So, in the k class case, we want to find a k minus one dimensional subspace onto which we want to project the data, right. So, that is fair enough. So, it is once again essentially I am thinking the facial linear discriminant, think of y as W transpose x plus some b, that W gives me the one dimensional subspace. Now, this y will be a k minus one dimensional subspace. The issue is now in the one dimensional space, finding the separation is quite straightforward. How to rate different one dimensional subspaces in terms of where the data of the two classes are well separated. So, we have to do a little more work on suitably generalizing the so called within class and between class scatter matrices, and so that we can find once again appropriate objective function. The details are complicated, and at least for this course we will omit them, and it is there in the reference textbooks that were given at the beginning of the course. But the basic idea is just this, we find a appropriate k minus one dimensional subspace on which we project the data. Okay. So, this kind of completes our discussion of all linear classifiers. We have considered various methods of learning linear classifiers and linear regression models, and we have considered all the algorithms in great detail, and also seen how they can be generalized to the vector case in the regression and the multi-class case for classification. Okay. So, what have we done so far? We looked at some specific cases of linear learning classifiers given the training data. We looked at two major things so far. One is the optimal base classifier and how to estimate class conditional densities for implementing base classifier. That is one way of, but of course, base classifier can also be viewed as a discriminant function, as we already seen. So, we can think of that also as a discriminant function. The only difference is it may not be linear. Okay. But if we can estimate class conditional densities, we can implement the base classifier kind of discriminant function. The other major chunk we looked at is various methods to learn linear classifiers. We looked at perceptron, least squares, LMS, logistic regression, facial linear discriminant, which I called FLD here. So, all these once again various ways of learning linear models for classification regression. Now what we will do is we take a look at we take a more generalized look at the problem of learning classifier. Now that we at least got some algorithms, we seen how the learning goes in practice, what the algorithms do and so on. We can actually step back and ask what is common to these algorithms, and then look at some issues of whether we are learning the right classifier, is there such a notion as the right classifier, how do we know what we learned is correct, and issues like that. Okay. In the very beginning of the course, we talked about generalization, right. We looked at the problem of designing classifiers as essentially one of learning from examples, right. We started with learning from examples as the basic issue. So, given training data, so you are given, say in the classification 2 class classification case, you are given feature vectors of class 1, feature vectors of class 2, and you are essentially be asked to say what is common to all the feature vectors of class 1 and distinct from feature vectors of class 2. There are various ways of representing this distinction. Say for example, linear discriminant functions is one way of saying is what is common to all feature vectors of class 1 is that if I use this w and w naught, then w transpose x plus w naught is greater than 0 if x is in class or in one class, less than 0 if x is in the other class, right. So, essentially given the examples, we want to learn some general principles by looking at the examples. Okay. So, that is what we have been doing. Given training data, we want to find an appropriate classifier. We have some algorithms for finding classifiers of certain structures. Okay. Now, what do all our classifiers amount to? Amount to searching over a family, some family of functions to find one that minimizes error. For example, our linear classification learning algorithms all, they are looking at a particular restricted class of classifiers, the restricted family of classifiers, namely linear classifiers. So, among all linear classifiers, that means among all w comma w naught or all vectors w, let us say augmented all vectors w. So, each w represents a classifier. So, all vectors w is a family of classifiers. We are asking among all vectors w, which gives me some minimum error over the training set. Error is how we define. So far, we only looked at squared error, so to say, but does not matter. We are looking for one classifier or a family of classifiers that minimizes error over training set. Right? For example, linear least squares, we are searching over the family of linear classifiers for minimizing square of the error. Okay. As we also discussed earlier, performance and training set is not the real issue. For training set, we already know the class label. So, predicting the correct class labels and training set is not the issue. It is like solving example problems in your maths course, just so that you are testing yourself whether you understand or not. And one hopes that by solving all the example problems well, you do well in the test, right. So, in the same way, what the learned classifier should do is to perform well on new data, right. How do we know if the classifier performs well on new data? This, as we considered earlier, is the issue of generalization. Does the learned classifier generalize well? You have seen a lot of examples. By looking at the examples, have I generalized it well, so that I learn the general principles, so that now I can classify any new pattern. Okay. So, what we are going to do next is look at this in a more formal sense, right, which provides us some way of asking some formal questions about generalization, and in the process give you some idea of what is called statistical learning theory. Okay. Our treatment of statistical learning theory has to be necessarily simplistic, because we are not assuming too much mathematical background for this course, but we will look at the formal statistical learning theory. Okay. Let us quickly look, before we go there, the formalism will start next class, but before we go there, let us just try to get some intuitive idea of what we are looking at. In practice, of course, we can always assess the generalization by looking at errors on a separate test set, just like the way we look at whether students learned well or not by giving a test. Right? After the classifier is learned, we can give extra data, which is called the test set. That data also has labels, so I can calculate errors. So, I just run the classifier on the test set and ask whether it does well. Since the test set is not used for training, error on the test data could be a good measure of the performance of the learned classifier. This means that of course, we should have more data, right. We can't use all the data we have for training, and if we let away some data, maybe we don't have enough data for training. We will come to all these issues later on. We will consider these also later in the course. So, these specific issues of practice we will consider later, how one actually assesses in practice a given classifier. But right now our focus will be on more theoretical analysis of how to say whether learning algorithm would generalize well or not. Given any data, can I say this algorithm would generalize well and that algorithm may not generalize well, and so on and so forth. Okay. So, to ask what this means, let's take a very simple example of regression. Let us say we have one dimensional data x I, y I, both x and y are on real line. This is the standard least squares curve fitting problem that all of us have solved in class 12. You are given points x and y, and you want to find a good functional relationship y is equal to f of x, right. We want to run a function so that we can predict y as f of x, right. Simplest regression problem, we can use least squares for this, right. Basically, of course, you have to have some particular form for f. So, let us say we choose a polynomial function. We do not know what m, but we choose a polynomial function w0, w1x, w2x square, wmx. As we have seen earlier, this easily fits into linear least squares, right. Linear least squares does not necessarily mean that the function is linear, it is only linear in parameters. So, we have already seen when we did least squares regression that this exactly fits into linear least squares problem. So, the question is, what m should we choose? We already asked this question at an algorithmic level. We said that obviously we do not know what m to choose, just because if we choose a very large m, we may artificially think we are getting low data error. So, we introduced the regularization, which can be viewed as a Bayesian approach to estimation, but that is an algorithmic thing. We said, okay, we take both data error and some regularization term, and there is a regulation constant. So, these algorithmic issues are important, and ultimately that is how we are going to control generalization. But first our focus is theoretically understanding why we need such a regularization. Okay. So, essentially one way of thinking of it is, what m should I choose? Can our data error tell us what m is proper? Of course, we already know it cannot, but let us say what it means. Suppose I have two m's, m and m prime. That I get less error for m prime compared to m does not necessarily mean m prime degree polynomial is better than is a better fit, right. Suppose you give me the data, I fit a straight line to the data. Let us say for the best fit straight line, I get my squared error as some 2.16, right, some number. Then let us say I fit a quadratic now. Obviously, quadratic possibly may fit better. So, let us say I got 2.09 as the error for the best fit quadratic. Does it mean that quadratic is a better fit than linear? If you think 2.09 is too close to 2.16, let us say for quadratic I get 1.98. Is it better? Is 1.94 better? How do I decide? Can I say that looking at the errors, is quadratic better than? No, in its simplicity, of course, this cannot be answered, because we know if I got n points and I fitted a nth degree polynomial, I will get 0 error. But obviously, nobody would think of saying the nth degree polynomial is best fit for n points. It is like saying, given 2 points, I can conclude that the relationship is linear, or we cannot, right. So, how do we address this issue more theoretically? If for a particular m we get very low data error, can we say it is good? Obviously not. As we just now seen, if I fit a nth degree polynomial, I get 0 error. No, nothing can be lower than that, but that is not good. I can ask the other way. How many examples should I have for me to believe that low data error is means there will be low test error? For example, if I am fitting a straight line to 100 points and I got 0.001 error, I can have fairly good confidence that straight line is the right thing. But if I got the same thing with only 2 or 4 points, I do not know whether I got the right straight line. Right. So, one way of asking this is, if I am fitting a particular kind of function, how many examples should I need before I can believe my data error? Right. So, that is certainly one important question to ask. We know that, say for example, if I want to fit 100-degree polynomial, I intuitively know I need more points than if I want to fit 3rd-degree polynomial. But can I formalize this for a particular class of models that I want to fit? How many examples would I need for me to have confidence in my data error? We also know that suppose I say set to all possible polynomials, then no matter how much data I have, I can never get anywhere. If I do not fix m, but I say you said, of course, right now we do not know how to do that, we only know least squares algorithm. So, we can know it only if m is fixed, but let us say I have a learning algorithm which can set over whatever I want. Then if I say set over all possible polynomials, then obviously no matter how much data I have, I would never get a good fit, because I always overfit. I will always, if I have n points, I will always pick the nth degree polynomial, because my bag of classifiers has polynomials of all degrees. So, we know intuitively that we will never learn anything if we do not restrict the class of models over which we fit. Can we formalize this? Can we make this notion more precise? When is something learnable? When is something not learnable? Okay. Because there are many ways of handling this. There are things called minimum description length principle, Vapnik-Chenoweth's theory, and so on. So, what I am going to do is, starting next class, we will have a brief review of this in a intuitive form first, and then we will only look at the so called Vapnik-Chenoweth theory of statistical learning. That is the only formalism we will consider, which at least lets you understand what model complexity mean, why model complexity term comes, where the regularization issues come up, and it will also give you some idea of how many examples are sufficient for us to believe our data error. Okay. So, that is going to be our plan for the next few lectures. Thank you.